In this video, we're going to talk about some translation review and maybe one new thing, and then we're going to talk density curves and the Z-statistic. So, our class data concerning height, you can see here off to the side, and I've brought in just a ton of stuff here, different screen captures of my calculator. So hopefully you are at the point where you would just put this data all in list one and do one variable stats. So you can see, I'm just going to quickly fill in the mean was 68.5. The median is 69.5. The standard deviation, remember, we saw the sample deviation, we use this, 4.23, okay? So, 4.23. The IQR, so we do Q1, Q1 minus Q3, so down here you can see we've got this 72 minus 65, so the IQR is going to be 7. The variance is actually, sorry I didn't write that, 4.23. The variance, remember, is the square of the sample deviation. So we would take the 4.23 and we would just square that. So 4.23 squared. So it's probably going to be 17 point something. I'm just going to write 4.23 squared. In terms of the distribution and the shape, if you actually graphed it, if you get a plot of it, let me pull one in quick. Here's a modified box plot, so you can see there aren't any outliers. To me, it looks pretty symmetric. Okay, so I'm going to say symmetric. Just do that. The percentile rank of someone that is 71 inches tall. So here I go to 71, and I end up, if I count, I have 13 people below that. So remember, percentile is always the percent below, so 13 out of the 19 are below. That is approximately 68%. Okay? So again, hopefully you're just kind of doing all of this with the with your calculator and doing the one variable stats. You shouldn't need to do much more than that. Okay. Now, the next question is, if we wanted to convert every piece of data to be in centimeters, which of the following would change and how? Well, first of all, you can see my little conversion here that it's 2.54, so it's a multiplier. Okay, so if you wanted to actually do this, you could by going into your lists. I did it right here. And you can see I went into list 2 and I highlighted it. And in list 2 I said I'm going to take list 1 and multiply it by 2.54. And when you hit enter, it will actually do that for you. It will fill those lists. So then, if you wanted to do one variable stats on this new set of data, you get your your new numbers like this. And I think, for the most part, you could see that the change is going to be, it was 68.5, now it's 174. It was multiplied by 2.54. The median was 69.5, now it's 176. It was multiplied by 2.54. The deviation was 4.23, now it's 10.5 or 10.74. It was multiplied. The IQR, right, was 7. Now it's, 17, so multiplied by 2.54. The variance. The original variance was 4.23 squared, and I said, oh, it's probably about 17 or something. But notice that the new variance right here is going to be 10.74 squared. So this new variance, it's usually given this symbol, this is going to be well over 100. This is going to be approximately 17. So it is not a multiplier of 2.54. Instead, because the variance, remember, is the answer to deviation before the square root, this is the only thing we've experienced so far that is not a multiplier of 2.54. It's a multiplier of 2.54 squared. So essentially, you would find the deviation, multiply it by 2.54, and then square that to get the variance. You don't multiply the variance directly, you multiply the deviation. Okay, every other information up until that point, the mean is changed, the median, the deviation, the IQR, up to variance, everything is changed simply by a multiplier of 2.54, but the variance multiplied by 2.54 squared. The shape, well, the shape is not going to change. It's still going to be the same shape. And the percentile rank of that 71-inch tall person, well, once we figure out what their centimeter height is, that will also not change because every piece of data has been multiplied by the same amount. So, one thing we talk about quite a bit in this class is density curves. And density curves are a way to talk about proportions or probabilities or percentages of a population. And we use this curve and we kind of draw it, and the area inside corresponds to the proportion of the population that belongs in a category. So obviously, if we're talking about a proportion, the total area of the curve must be 1, or 100%. So you can see down here, I've just drawn kind of a silly density curve. It really has no meaning, but it's between 0.1 and 0.5, and you can see the y values here. So if we add them up, we could say, well, each box is 1/10, so 1, 2, 3, 4, 5, 6, 7, 8. This would make 9, and these two would make 10. So 10 boxes of 0.1 is an area of 1. So my first question is, what proportion, if I picked someone from this curve at random, what are the chances they lay between 0.2 and 0.3? Okay, so let's just go over here. Here's 0.2, here's 0.3. So you can see, using area, that's 0.3. Okay. The next question, what is the chance, the probability that they were above 0.4? You see, that's this bunch right here. So that area is 0.15. And finally, the probability that this random person or random thing that had this density curve was in between 0.2 and 0.5, well, we'd have to add all of these up. So there's 3, 4, 5, 6, 7. So it's 0.7. Now, as I said, this is kind of a silly density curve. Let's talk about one that's maybe a little more realistic. You have a function on your calculator called rand. And here's how this works. If you go to the math button and then scroll over to PRB, you'll see the very first thing is rand. And if you begin hitting enter, you get random numbers between 0 and 1. Just random decimals. Okay? So, get this out of here. This curve gives you random decimals from 0 to 1. And all of those numbers between 0 and 1 should have an equally likely chance of being picked. So it's a uniform density curve. And because we know the area has to be 1, the height of this must be 1 as well. So I'm going to try and color code this again. This first one, what are the chances that a randomly picked value from the rand density function is between 0.1 and 0.5? Well, here's 0.5. Here's 0.1. So the chances, we use the area. And there's 4/10 of area inside there. So it's 0.4. Now, what are the chances that a variable is above 0.3? Well, of course, how much area is above 0.3? 0.7. And finally, what is the area, or what are the chances that it's below 0.42? Well, that's 0.42. So just using the area. This gives us a way to talk about, proportion or probability using, like I said, using this curve. Now, the final question I'm going to ask is, what's the probability that a randomly selected value is equal to 0.5? And the answer is 0. And there are two ways to think about this. The calculus way to think about it is to think, well, if we're doing an area of this RAND function, what's the area between 0.5 and 0.5? Well, there is no area between 0.5 and 0.5. That's the calculus way to think about this. The non-calculus way, the probability way, is to say how many different outcomes are available between 0 and 1. And the answer is there are an infinite number of numbers between 0 and 1. So when I say, well, what are the chances that I could pick from a random number or any random number and pick exactly 0.5, well, that would be 1 divided by an infinite number of outcomes. So that's why we say that probability is 0. We'll come back to that idea, but I just wanted to kind of hint at it now. The last thing I want to talk about in this video is what's called the Z-Statistic, or sometimes referred to as the standardizing score. And the standardizing score is really a way of putting things in relation to other things that maybe belong in the same category. For example, maybe the ACT in the 1980s had an average of 20 with a standard deviation of 5. And maybe now the average is 21.1 with a standard deviation of 4. So saying that I got a 30, that's different now than it would have been in 1980 relative to all the other people taking the test. Your percentile rank would be different. Okay? So this is a way of saying how we can compare to the average and standard deviation within a category. So for us, if you recall, just to look at the calculations, our mean height was 68.5. Standard deviation was 4.23. Okay, so the Z-score for someone with a height of 71 inches says, well, 71 minus 68.5 divided by 4.23. So what this calculation represents really is how many deviations away from normal or from the average was this person. How many deviations away from the average? So the standard or the Z-score for someone with a height of 63 would be 63 minus 68.5 divided by 4.23. And you'll notice this answer will be negative, and that's because this person was below the average. They were deviations under average. Let me show you another example with this, and that I think will explain why it's called the standardizing score. So this is the Z-Statistic. This is the information for baseball players that at the time they set the home run record. So in 1927, Babe Ruth set the home run record in a season with 60 home runs. In 1961, Roger Maris reset it. 1998, Mark McGwire reset it, and in 2001, Barry Bonds reset it again. Again, this is home runs in a single season. And next to it, you can see in the league, or in the major leagues that year, what was the average number of home runs hit, and what was the standard deviation for those players. So for something like Babe Ruth, you could say, well, he hit 60 home runs minus the mean divided by the standard deviation. Roger Maris, 61 minus the average divided by 13.4. Mark McGwire, 70 minus 20.7 divided by 12.7. And Barry Bonds, 73 minus 21.4 divided by 13.2. So in each one of these statistics, these Z-statistics, what we're getting is how many deviations above the average player for their time period were they? So it's comparing them really just as for their era, who was the best home run hitter. And I actually did calculate these. Let me drag the calculations in right here. And you can see that Babe Ruth was over 5 deviations above his peers, whereas the rest of the players were, between 3.1 and 3.9 deviations above. So relative to the time period, Babe Ruth was the best home run hitter, even though Barry Bonds had more home runs.